And so we had like a suitcase thing. So up here would be the screen, and then the reel-to-reel would be down here, and it had a little projector so that they could see it. And it would just loop, you know, you only had so much, and it would just loop over and over again, and they could see it. So very difficult to see, but definitely an increase in patient exposure. Your interventional radiography exams tend to be your higher risk exams because they're, again, injecting contrast media under pressure. If you're going to have an anaphylactic reaction, that is when it typically happens. We're going to study a lot of contrast media studies in this class, and you won't have the experience with anaphylactic reactions as I have had in the past, because the contrast media is now non-ionic, right? I always want to say non-ionic. It's non-ionic, not
Ionic?
iodinated.
Oh.
It's like I get those mixed up. Non-ionic, so you won't have that issue, and that's why they were developed, is because of the anaphylactic reactions that we always had. And so when you put contrast media directly into the bloodstream under pressure is when the chances of an anaphylactic reaction happening. So your interventional studies tend to be your high-risk studies. And then who's having an interventional procedure? People who are already at high risk because of, you know, coronary problems or atherosclerosis or whatever. So a lot of times, not a lot of times, but that is the time when, that's when my first patient passed away that I had, was during an angiography study. So, anyway, enough about that. So again, we're looking at, when we're looking at the image on the monitor, what are we looking at? We're looking at a fluorescent screen glowing. Okay, that's what we're looking at. That is not a radiographic image. Barium is black, air is white. When we take a radiographic image, is the reversal of that. So let's look at resolution and contrast. Simulation is kind of like your and we use it in fluoroscopy, or we use it when talking about screens. It's like quantum model. It's your quantum model. You get scintillation when you have an insufficient number of X-ray photons, which is in radiography. Quantum model is the same thing. Okay. So what happens? It decreases resolution again, just like quantum model does. And how do you get rid of it? In both cases, you increase the tube current or increase the mass. Increase the mass, the tube current. When we talk in fluorography, we don't say mass because of you have fluoro time. That's continuous. So we tend to talk about MA only when we talk about fluoro. So that's why you're not seeing mass up here so much. And that's why you only see tube current. What is tube current measured in?
kV?
No.
Oh.
Thank you, no. Thanks for saying that, but that's incorrect. Well, I just went over this with the senior students, the interns, for a review. Current is measured in amperage, or in a variation of that, milliamp. So your two classic questions are, you remember this? I'm not going to draw it all out, but you have your auto transformer, your step-up transformer, your rectification circuit, here's your X-ray tube, and then down here you have that's your filament, and then you have your filament circuit down here. So up here, all of this circuitry goes to the X-ray tube. Okay. The question is, what is the X-ray tube circuit current measured in? And what do you use in radiography to make an X-ray? You use milliamps. X-ray tube circuit is measured in milliamps. Now the filament, do you remember how much it takes for electrons to be boiled off at the filament in an X-ray tube? Okay, I'll remind you, 3 to 6 amps. Okay, so the filament circuit is measured in amps. The current in the tube circuit is measured in milliamps. Does that ring any kind of bell?
A little bit.
Like 100 years ago?
A little bell.
Kind of
Then again, I did take it with Trong, so.
Well, he would have taught you the same thing.
Yeah, but it was a long time ago.
You're talking about Tron?
Mhm. That class was a doozy.
Yeah, we took it together.
Oh, did y'all?
Yeah.
Well, did you not like it? Does he not have the best PowerPoint presentations?
Yeah,
Very
it's-
detailed.
It's hard to,
Yeah.
Understand them?
yeah.
My favorite's when he puts a timer up during your exam.
Okay,
Yeah.
if you go into ultrasound, that's what they do in ultrasound. They time them with a timer. Nancy had this thing, it was like this big, and it was digital. I'm like, what the heck? She goes, oh, that's for our tests. She did have an egg timer, and then now the students like it because she can put it up on the wall. It sticks to
It makes
the
you
wall,
more-
and they can see it.
Makes me
Yeah,
nervous.
it kicks up your anxiety.
Well, so I'm just saying,
Like,
everyone,
dude, I got-
everyone
I
is
got 5 more
different.
minutes.
Everyone is different with the way they teach. You
Yeah.
just had to kind of go, there's advantages
Definitely
and
kept you on your
disadvantages
toes,
to
man, I'll tell you
everybody.
that.
Yeah, I mean, it's just think when you take your ARRT exam,
Yeah.
you'll finish it in time. It won't be a problem. Okay, so I kind of got off side there, but anyway. Resolution. Typically, the input phosphor is cesium iodide. You've seen that before. You've heard that before. The output phosphor tends to be zinc cadmium sulfide. It doesn't have to be that. It can be cesium iodide also. It's just what it tends to be. So cesium iodide for the input, zinc cadmium sulfide for the output phosphor. Contrast. We have some issues with contrast, and again, you're seeing all the different shades of gray that you need to see during a fluoro exam. So what happens, okay, so here we have our electrons coming from the photocathode to the output phosphor. Here they come and they hit the output screen. Well, some of them are scattered in the backward direction. So you get this retrograde light scatter, and you get these retrograde electrons that are coming in the backward direction. We don't want that. We want all the electrons to hit the screen and all the light to go in this direction. Well, phosphor crystals fluoresce in 3D, so the light's going in all directions. So some of the light from the output screen is coming back this way. Not all the electrons are converted to light, so then you have some unconverted, electrons. So unabsorbed electrons and retrograde light flow diminishes our contrast. So those are the two issues that we have to deal with. And so what is done, a little piece of aluminum, remember, is placed at the output phosphor to absorb any of the light or electrons coming in the backward direction. So that's how that is corrected. We have the aluminum here at the output phosphor for that reason. And again, we can adjust contrast a little bit on our monitor, on our computer monitor, just like you can on your computer monitor. So digital fluorography, look at this, 1970s. When did we digitize X-rays, routine X-rays? It was like
90s?
Yes, late 80s, early 90s that it became more prevalent. And so, but fluoroscopy and again, all the other imaging modalities, all they did was add a computer to the system. So they replaced the TV camera with the CCD, put a computer in there, and that made it digital. So now instead of looking at a TV monitor, we're looking at a computer monitor. Typically 2 monitors are used during digital fluoroscopy. It doesn't have to be that way with all of them, but I don't know, at your hospitals, do you have 2 monitors or 1 in your rooms?
Well, 1 monitor for the doctor, then the monitor in the control room.
Okay, so that's basically 2 monitors. 1, okay. That's all right, that's fine.
She's like, we have half one.
You have 1 monitor for editing patient information. The right monitor tends to be a real-time image. So here's a typical, this is a C-arm, like you'd be up in, they look like they're up in surgery, kind of. And then here are the 2 monitors on a roller transport thing. So this would be more your portable fluoroscopy system. I don't know, in your rooms, are the monitors hanging in your in the radiography department, are the monitors hanging from the ceiling? Or are they on a cart
On a
that you
cart.
can kind of move around? So the doctor can move it to where they can see it while they're doing the exam. It's gotta be portable. Subtraction angiography or radiography, it tends to be with angiography procedures, is where we reverse the image and then subtract out the bones. So, and that used to be done a lot differently than it is with the computer, but it's all computer generated. So you have an image, a radiographic image, then you have your mass image, and then you put those together. Let's see how it goes. You have one image without the contrast media, and one image with the contrast media. One image without, one image with the contrast media. You put them together and subtract everything out that is the same between the two images. So everything's the same except for the contrast-filled vessel. And so can you see a little bit of the ribs and maybe the clavicle right there? It's not the best subtraction image right there, but what's happening, unlike a regular x-ray where you'd see these bones very clearly, they subtract them out, so now all you're looking at are the vessels. This isn't too bad just because of the fact that they're large vessels, but you can imagine cerebral angiograms, cardiac angiograms, where you're getting very tiny vessels and the overlying bone can obscure something that may be going on. So what subtraction angiography does is subtracts the bone out, all the common anatomy out, so where you're just like with this. We usually say DSA, digital subtraction angiography. So I don't know if you've seen any of that in your department, but when you'll get to rotate through there and you'll be able to see some of this. It's pretty exciting and pretty neat. Now, Dr. Freneza, you know, is an interventional radiographer, so he would be able to talk a lot more about this than I am able to. I've done it, but that was his forte, so. So now this, let's skip the first one. Let's skip that.
Like delete it? Skip it?
Well, I don't know. Let me come back to it. Let me just come back to it. Don't delete it yet. We're skipping it.
Yeah.
I can't decide what to do with this. I really can't decide what to do with this. I've researched this. I've talked to other people who are, experts in this, and they'll say this statement, but then what happens? Okay, so the generator in digital fluoroscopy operates in 100 MA. What did we learn earlier? It was 3 to 5 MA, right? Okay, when we were doing our digital fluoroscopy in our room, and I asked you to come out and read the MA reading, who was that? I don't know who did that.
It was me.
Okay. It was, I think it was like
1 point
1.9
something.
MA.
On our
So it
PowerPoint
was-
though, it says 1 to 5. It doesn't say 100.
Yeah,
It doesn't say
Right,
100.
Right.
Okay.
Okay, that's my point. When you read Bashang, he makes a statement. I've not found it anywhere else. I may have found it online, but I have nothing to support that. Even in the specs on the Philips equipment, I went to look through to see what, and they don't have it. So while you read that and it says that, I'm personally not convinced of that.
Maybe they forgot an F.
Maybe so. Maybe so. But, so I never know what to do with this. I never know what to do with it.
What should we do?
Because I don't know. That's a good question.
Should we learn it or ignore it?
I think what we'll do is let's delete that for the time being. If I were to ask you, what is fluoroscopic MA?
1 to 5.
You're gonna say 1 to 5, 3 to 5, less than 5.
You actually changed it.
MA. Did I?
Yeah, on ours,
Okay.
it doesn't say 100.
Oh, okay.
Yeah.
Well, I need to catch up. Every year I go back and forth. Every year I go back and forth. I never know, that's what I'm saying, I never know what to do with that information. Okay, so, forget that. Pulse progressive fluorography. This is great. Back in my day, fluoro was 100% on. You turn it on, it's 100% on the whole time. Now, it's pulsed, but it's pulsed so fast that your eye doesn't catch it. So that greatly reduces patient exposure by doing that. So the beam is switched on and off and is pulsed. Now, our room is not like that. The room that we have here, again, looking at the specs, we don't have that. We don't need to have that, do we? I mean, we don't do fluoro on real patients, and we do fluoro a whole, 5 minutes a year. So, so we don't have that. So you can get it or not. Okay, so, but I would imagine all your hospitals will have the pulsed X-ray beam. Image acquisition rates, this can be changed. We do have buttons on our equipment, and so look at your equipment, look at the buttons and see, some of the things that you can see. I know we have 3/S, so that means 3 images per second acquisition rate. Or it can go up to 10 images per second. So it can change. So like for an esophagram, you may want to go higher to capture all the motion. If you're doing an upper GI, is slower, right? You can go, a lower image acquisition. Let me ask you this, as your image acquisition rate gets higher, what do you think happens to patient exposure? It increases. So it just depends on what you're doing. Some doctors may not change that. They may use 3 images per second acquisition rate for everything. I don't know. Ask your radiologist. After an exam, you might ask them, do you ever change your acquisition rate? They'd go, oh, look at you. You know stuff. Well, you know what? And they may not know. I mean, sometimes we do things out of habit. Like for an esophagram, we go here. For upper GI, we go here. And that may not realize why or remember that they were doing it. I remember asking Dr. Keong at Hoag, who's my Hoagie. I asked Dr. Keong, I said, when we were talking about QA for monitors, and I said, do you QA your monitor? Or does someone come in and do that? He goes, no, we never QA our monitor. I go, really? I go, Doctor, I think that they do, and you just don't know. I said, you need to find out. And he called me, and he said, they do it every day. He just didn't know that.
Right.
It was done through the company that they have their system with, and they performed the QA. So he goes, oh, yeah, it's done every. I go, now that makes sense. So sometimes things are happening that we're not aware of, and nor does he care.
Yeah.
I mean, he only looked it up because I asked him to, otherwise, who cares? As long as it's doing what it's supposed to do. And so I want you to know, going back here, I might ask you, what are image acquisition rates? What's the range, 1 to 10 per second? What does the pulse X-ray beam do for patient exposure? I will ask you what the interrogation time is, and that's the time, if the beam is switching on and off, if it's pulsing, it's on and off, so it's got to have time to get to, be on and then to turn off. So that's the interrogation is the turn on time, and the extinction time is the turn off time. So these are going to be extremely, extremely short, 1 millisecond. Duty cycle, fraction of the time that the X-ray tube is energized. Oh, I wish I was an X-ray tube or a fluoro tube. It's usually 10%. So, duty cycle, and we have this in ultrasound. The ultrasound beam is the same way. The ultrasound beam, of course, is pulsed. So duty time. So if the duty cycle is 10%, what is your duty cycle? The time that you're working. So let's take a training tomorrow. You're going to clinical training tomorrow, and you're there 8 hours. So what is your duty cycle? 8 hours out of a 24-hour day, that's 1/3. So that's 33%. An X-ray tube works less than you do. Okay, to put it in perspective, it's really generating very little energy to do what we need it to do. So, hopefully that leaves your mind. Remember how you were freaking out last week? Being in the room and you had your lead aprons on and we were in the room during so I want you to have a healthy respect for radiation exposure. I don't want you to be afraid of it. So looking at all the things that we do to reduce exposure, let me ask you this, do your radiographers at the hospital seem afraid?
No.
Do the doctors, well, wait until you get a surgery, or you're doing the C-arm and one of the doctors goes, I don't want that lead apron, I'm 80 or 60 or whatever age, I'm way past, there's that extreme too, so there's an in-between and that's where I want you to be. I don't want you to, when you're beginners, you tend to be so afraid of it, and then when we are seasoned, we tend to be too lackadaisical about it. So there's an in-between in there. So I just want you're learning about all the things that we do to keep our doses low for our patients primarily, and in doing so, we keep our dose low. So, so those are some of the things you need to think about with your low exposures. So don't be so afraid of it. Okay, the CCD, this is what we're talking about, the CCD. Replaces the TV camera tube, is mounted on by the output phosphor. A couple ways it can be connected to the output phosphor, either through fiber optics or by optical lenses. It's very small and rugged. We've talked about that before. It has a high DQE. What does that mean? A high detective quantum efficiency, meaning that it's very sensitive to light, which we want it to be, light coming from the output phosphor. The more sensitive it is, the less exposure we can use. The CCD gives us lower electronic noise. You can imagine you have the image intensifier tube, which is an electronic device. You have the TV camera tube, which was an electronic device. You have the TV monitor, which is an electronic device. So, you have a lot of electronic noise, so if you get rid of that with the CCD, then that helps. Better contrast resolution than the TV camera tube. So it says 10 line pairs per millimeter. I don't think our eyes can even resolve that. So has a high contrast resolution. Lower patient dose, of course. No image lag. Remember when we were looking at the bigger body part to the smaller body part, we couldn't see it until the ABS kicked in and we saw the change. Okay, that's screen lag. Phosphors don't react as quick. Some phosphors react with phosphorescence and some phosphors react with fluorescence. Fluorescence is a quick response time. Phosphorescence is a long response time. So when for fluorography we want phosphorescence, a long fluorescence. So we see the image longer. That helps, right? But then when you drag the fluoroscope from one body part to the other, it takes a little while for the image to come up. And I say a little while, I'm talking seconds, but still, that's what we mean by image lag. So with the CCD, we don't have that. So again, what does that do? Lower patient dose. It says no maintenance, and look here, no pincushion effect. So that's not something that we have to worry about when we have digital fluorography. Lots of good things with that. This is what a CCD looks like, and it will be attached somehow to the output phosphor. So here is the fiber optics. This is to a TV camera tube, but it would be to a CCD. And here are the objective lenses that it can be connected to. Again, this is a camera lens, but it could also be a CCD. So either way, here's a CCD with fiber optics. Here's a breakdown of it. Look at that. Don't ask any questions. Okay, computer. The output signal from the camera tube, which we're not using anymore, is CCD, and then image acquisition rates, which we talked about already, 1 to 10 images per second. So we've already kind of talked about that. And then we talked about this already. Patient dose is reduced because of pulsing of the beam rather than continuous. Now, looking at the patient, this is just an example. This is not, for every patient in every exam. So again, I don't want you to, this is out of your textbook. But just to give you an idea, conventional is what I grew up with, and digital is what you're growing up with. In the, not with the screen, still image intensifying tubes, but what we call conventional. 5 minutes of fluoroscopy time, that's 5 full minutes, which is a lot. 20 rad. Look at what happens with digital. It's cut in half because the beam is pulsed. And of all the things we talked about, duty cycle and all sorts of things, just looking at the fluoro time has been cut in half using the CCD being digital and all that. So that's amazing right there. 3 spot films. Now this is using the cassettes with the film in it to take images. If we took 3 in normal mode, that's a little over half a rad. Okay, with digital, looking at that, again, yeah, much less than that, 1/3. And then doing 3 spot films in mag mode, you can go up to 1 rad. Again, with digital, very little difference. So, again, the dose has been about cut in half from what we had before. And I've turned off the lights in here. Did I glow in the dark? So you're going to be, much less of any generation that we've ever had before. Okay, so it just gets lower and lower. And then with digital radiography compared to, non-digital, it's even less. So your radiography profession is really going low dose. We're already there. Okay, flat panel image receptors. These are so cool. These are so neat. I do not think you have them in your hospital. If you have them anywhere, it might be with your portable fluoro units. Your portable C-arms may have a flat panel detector. I don't know. But look for this. Again, you're looking at cesium iodine and with the silicon. Remember, it's like your digital detector in your tables for digital fluoroscopy, for digital radiography. They're your detectors, right? And they're much smaller and lighter than an II tube. You don't have the veiling glare, the distortion, the vignetting. You don't have all of that with your detectors. Does not degrade with age, which is amazing. Fluoro tubes degrade about 10% per year is the average rule of thumb. They don't last forever. Sometimes they last longer than we want them to, right? The flat panels don't. The image is square, just like our monitors. Instead of having a square computer monitor with a circle image, you would see a square image. So, why haven't we done that from the beginning? But anyway, I don't know. But anyway, this is what it looks like. So you don't see that big image intensifier tube. So here's the fluoro tube or X-ray tube underneath, and there's your flat panel detector there. So the whole II tube is gone. It's a detector, and I don't know all the physics components of it yet, but these are the newer flat panel detectors. So pretty cool. That will be your future in fluoroscopy, is to see those. And you can see, still they have the 2 monitors here. And it's like, really, I'm sure there's a low weight limit to this. Look, this thing is mounted, I guess, on the floor. This is just a mock-up. I shouldn't even judge that. But look at the table. Yes.
We had a patient who was sitting out in the hallway, and then we had the techs kind of running around trying to grab the person doing the C-arm. And they're like, "Is that your patient out there?" And she's like, "Yeah." She's like, she might not fit in the tube. So I wasn't around for what they ended up doing, but she wasn't able to fit in the C-arm. I don't know what they did, but.
Patients, every table, every X-ray table, every CT, MRI, any of those tables, they all have weight limits. They all have weight limits. So the challenge is, when you can't get a patient on the table, what are you going to do now? And I feel bad because they're the people who really need the study. study done and more compromising. So in my case, in my experience, it has been every time a poor study because we couldn't get them where they needed to be because of their weight. And that it's not an optimal study, you know, so it's a bad situation. And yeah, that's what we have to do. Here's another one. This is where, this is where the tube is on top, and here's your flat panel detector underneath. So a lot, you know, more lightweight, streamlined. You don't need as much room. Okay, fluororegs. I got these from, these are mainly